I just want to open by saying that what I am doing here is very dangerous. The voltage and the current is lethal. If you touch the water while the voltage is on, you can go into cardiac arrest and die. Please don't try to duplicate this at home. Ever wonder how someone can get electrocuted in a bathtub if electricity is supposed to take the shortest path? It would sound like the current would just go straight from one wire to the next, and you should be safe over here. But that's not how it really works. In reality, current takes all available paths. It doesn't just flow from here to here, but it flows all around. Where the resistance is lower, more current flows. Where it's higher, less current flows. But as long as there is any conductive route, some current will travel through it, including through the water, the tub, or even a person. Pure water does not conduct electricity very well. If I go ahead and this is set on resistance, and we put it in, we have about 1.1 mega ohms. There is no salt in here. And let's just see how much current this will actually allow. I have this connected to my wall outlet through a variac. I'm going to turn it on. I'm going to turn up the voltage slowly to 120 volts. And this is now 120 volts. You do not want to put your hands in this water right now. So that's 13 milliamps going through. I've just turned off the voltage. I've unplugged it. And I'm just going to add some salt. This sets up some sodium and chlorine ions. We'll let that dissolve for a few minutes. It's been about a minute. Let's see what our resistance to the water is now. It varies a bit, but it's about 130-ish, sometimes as low as 80,000 ohms. It's looking more like about 120s, 140s. Now let's see how much current will flow through. I am going to switch it to a higher scale because I know what's going to happen. It's on a 20 amp scale. Let's increase the voltage. Going up to 120 volts on my variac. I'm now at 120 volts. And I have 1 amp plus of current going through that water right now. You might say 1 amp of current, 120 volts. Using Ohm's law, that means the resistance should be 120 ohms. But I just measured it, and it was showing 140,000 ohms. So there's a difference here. That the effective resistance of the water is based on the applied voltage and the current that goes through because of it. When I use an ohm meter, it puts a tiny voltage across the leads, and it measures the current going through. But when you have a much higher voltage and there are ions involved, this causes the ions to accelerate and colliding more frequently, reducing the apparent resistance, allowing much more current to flow than you would think. So let's get back to what I started to talk about, which is how you get electrocuted if you're standing here when you would think the current should just be flowing there. So let's apply our voltage across. initial assumption was if current takes the shortest path between here and here, you should be safe, like electricity flowing through a wire. Why would you get electrocuted here? But there's actually field lines. There's a gradient. There's a potential all around in space, in the air and in the water, where there is a voltage difference between any 2 points. The current, as I said before, takes all possible paths. So I'm going to put this on AC voltage. There is no voltage here at all. I'm going to turn on my voltage source again. I'm going to go back up to 120 volts. There is 1 amp plus of current flowing in the water. Notice that there is actually a voltage potential between these two electrodes in the air. There is 300 millivolts of voltage going across. And if I put it in the water, there is 5.6 volts across these 2 points. As I get closer to my actual voltage source, the voltage goes higher. You can actually see I'm actually breaking down the ions and generating gas, and the current's going up as I'm introducing more ions into the water. You can see the bubbles right in between. Voltage potential increases with the distance. So when my 2 points are very close that I'm measuring about 6 volts across about a centimeter of distance. But if I go to the ends, there's 60 volts here at the end. 80, 90 volts here. So there's voltage all in this entire pan. This could be a pool. And there's going to be voltage that is lethal anywhere in there. Very dangerous. So let's see how much current flows at 120 volts between a short distance. About 20 milliamps. As I get closer to the voltage source, it goes up to 80 milliamps. But watch what happens when I'm, say, moving further away and I'm separating the distance between the probes. I'm at 120. I'm at 80. I'm at 100 milliamps of current here, and that's lethal. Electricity, in closing, doesn't just take the shortest path, it takes every path. And in a conductive liquid like salt water, or anything that has some ions, this means the entire tub becomes energized with voltage potential through its entire volume. That's why water and electricity never mix, because once the water conducts, the whole environment is part of the circuit. So stay dry and stay safe and keep your appliances away from water.